Hi, I am Professor Jesús Toribio from the University of Salamanca in Spain. The title of my presentation is Hydrogen embrittlement of pearlitic steel in the presence of notches, a kinematic fracture criterion based on the notch tip strain rate. This is the beautiful logo of my university, the University of Salamanca, the oldest in Spain, more than 800 years old. This is the outline of my talk in 5 parts. 1 introduction, 2 notch tip strain rate, 3 experimental program, 4 fracture criterion, and 5 conclusions. Let's go to the introduction. The motivation of this work. It is well known that environmental assisted fracture EAF processes depend markedly on kinematic variables such as the strain rate, the dependent being non-monotonic for localized anodic dissolution or pure stress corrosion cracking, and monotonic for hydrogen embrittlement or hydrogen-assisted fracture. When notched specimens are used to study environmental assisted fracture, the local strain rate at the notch tip strain rate, is the variable governing the process. This is the strain rate in the vicinity of the notch tip or just at the notch tip, or as an average in the close vicinity of the notch tip, the local strain rate at the notch tip or the notch tip strain rate. Then the aim of the work is a numerical computation, finite element computation of the local strain rate at a notch tip that is provided, with particular emphasis on formulating a kinematic fraction model to describe the strain rate effect, the strain rate dependence in tests with notched specimen subjected to environmental conditions promoting hydrogen embrittlement or hydrogen-assisted fracture. The model is formulated by expressing the critical fracture parameter of the material as a function, as a universal function of the notch tip strain rate, which are one-to-one relationship between this material resistance and the notch tip strain rate, a geometry independent universal curve that governs the hydrogen entry. Let's go to the concept 2 of notch tip strain rate. In this work, I am analyzing 4 different, very different notched specimens with very different geometries, covering the wide range of stress triaxiality constraint levels in the samples. Geometry A, minimum depth, minimum radius. Geometry B, minimum radius, maximum depth. Geometry C, maximum radius, minimum depth. In geometry D, maximum depth and radius. With these ABCD geometries, we cover the full range of stress triaxiality levels, stress constraint stress levels, and thus thereby promoting different hydrostatic stress gradient governing the hydrogen entry in the sample, just to study the strain rate effects. This is the plot with the computations of the notch tip strain rate for the different geometries A, B, C, D. In the vertical axis, we represent the ratio from the local strain rate at the notch tip to the global strain rate at the sample ends, as a function of the global strain at the sample ends. We observe that in the 4 geometries there is an increasing trend of the local strain rate with the applied global strain. That is, the local strain rate increasing with yielding plasticity development in the sample. And this increase of local strain rate depends on the particular geometry. The higher the triaxiality level, the higher the local strain rate in the close vicinity of the notch tip. The higher the triaxiality constraint level, the higher the stress and strain concentration, the higher the notch tip strain rate evolution in the sample. Then the maximum triaxiality is achieved in geometry B. These results are applied to the modeling of experimental program of hydrogen embrittlement test on notched samples of pearlitic steel. Here, the experimental device consisting of a potentiostat and a 3-electrode assembly, reference electrode, saturated calomel electrode with a salt bridge, a platinum counter electrode, and the metallic sample reference electrode. Sample electrode. These are the experimental results for the 4 geometries A, B, C, D. The level of triaxiality constraint influences the results. In vertical, we have the fracture, the rupture load, Fr divided by the F0, fracture load in hydrogen divided by the fracture reference load in air, versus the global displacement rate in meters per second. We have in the 4 geometries an increasing trend of failure load in hydrogen with the displacement rate. The higher the displacement rate, the less the time for hydrogen entry and diffusion and deleterious effect on the sample, and the best the results regarding fracture load in hydrogen. There are 2 asymptotic values in all plots. Apart from this increasing trend with the displacement rate, we have the quasi-static test left-hand asymptotic value, in which for low displacement rate, the quasi-static steady state condition for hydrogen diffusion and equilibrium in the sample is achieved. Then we don't have a more damaging effect of hydrogen for decreasing displacement rate. We have reached the equilibrium condition for hydrogen metal equilibrium in the metallic lattice, and then we have the quasi-static test asymptotic left-hand side value. On the other hand, in the right-hand side part of the plot, we have the quasi-instantaneous test, in which even for this quick test, we have a deleterious damaging embrittlement effect of hydrogen due to the achievement of boundary condition for the hydrogen diffusion problem in the sample. With regard to fractographic appearance of the hydrogen assisted micro damage, this is the so-called tearing topography surface and evidence of hydrogen assisted micro damage in pearlitic microstructures. When we deal with pearlite, the effects of hydrogen at the finest micromechanical level is as follows. This appearance of tearing topography surface, a kind of very ductile, at the local microscopic level, apparently ductile or tearing micro damage due to hydrogen. It embrittles at the global scale, but it produces micro damage with tearing appearance at the micro scale. This is the hydrogen-assisted micro damage in the form of the so-called tearing topography surface, and evidence of hydrogen effects in pearlite. Let's formulate the fracture criterion. This is the kinematic formulation of the fracture criterion for the 4 notched samples A, B, C, D. Here we represent 2 dimensionless variables, dimensionless sigma, dimensionless stress, and dimensionless strain. The dimensionless stress is obtained from the critical fracture loading hydrogen embrittlement test with notched samples, by using also the critical distance concept, the tearing topography surface extension. In the horizontal axis, we have the average value of the local strain rate at the notch tip or its vicinity. The average value of the notch tip strain rate is a double average, a space and time average of the local strain rate at the notch tip or the notch tip strain rate. We take the instantaneous value of the notch tip strain rate and we average it in a space and time. The space average is computed over the extension of the tearing topography surface or hydrogen-assisted micro damage, critical distance concept, process zone or critical zone for failure in hydrogen. And in addition, we compute it as an average in time. along the test duration from 0 to the critical time or hydrogen embrittlement time. We obtain a universal curve representing the kinematic fracture criterion for hydrogen embrittlement, a single curve, dimensionless stress versus notch tip strain rate, dimensionless strain rate, as a universal single curve geometry independent. But of course, for the quasi-static test, we have different left-hand side asymptotic levels depending on the triaxiality. Then, for highest values of triaxiality B, we have the most deleterious damaging or embrittling effect of hydrogen. The higher level of hydrogen embrittlement is obtained for geometry B in quasi-static test with the maximum damage by hydrogen due to the higher triaxiality constraint level promoting hydrogen entry and diffusion by strong, very elevated hydrostatic stress levels. Geometry A also very high triaxiality level, the sharp notch specimens B and A, and regarding the blunt notch specimens C and D with the highest radius of the notch, we have softer, milder effect of hydrogen due to the not so elevated hydrostatic stress gradients. Then, for sharp notch specimens, we have the most damaging effects of hydrogen, and for blunt notched specimens, we have a milder effect of hydrogen. These are the asymptotic values. Outside this common trend, universal curve, kinematic fracture criterion for notched samples on the basis of the notch tip strain rate or local strain rate at the notch tip. With regard to the left-hand side asymptotic values for quasi-static test, quasi-stationary test, steady-state condition for hydrogen diffusion, equilibrium condition for hydrogen metal in the lattice is achieved for a very slow test, and in this case the asymptotic horizontal value depends on the geometry and on the triaxiality. But the order is really beautiful. It's BACD. It resembles BACH, the number of Bach, Johann Sebastian Bach, the genius, the best musical composer ever. Let's go to the conclusions. 1. In the slow strain rate testing with notched samples, local strain rate at the notch tip, and not the externally applied displacement rate, is the variable governing the environmental assisted fracture EAF process. Second, this paper provides definitions of the local and global strain rates in notched geometries by considering both the mathematical convergence of the method and the agreement between the model and the physical reality of the material. 3. Local strain rate at the notch tip depends not only on the material properties and sample geometry, but also on the loading process, that is, on the global strain externally applied on the sample ends. Therefore, the relationship between local and global strain rates is not constant, but increases with time, even for constant global strain rate. 4. Development of the plastic zone is quite relevant for the evolution of local strain rate. The importance of the sample geometry and the constitutive equation of the material, particularly the strain hardening capacity, is thus emphasized. 5. Local strain rate results are directly applicable to the modeling of environmentally assisted fracture. Then, usual fracture criteria under aggressive environments can be improved by replacing global strain rates by local ones. For hydrogen embrittlement, HE, space-time average of local strain rate are representative. Space average over the hydrogen-assisted microdamage or TTS region in pearlite, critical distance concept, and time average over the test duration or time to failure in hydrogen embrittlement test with notched samples. 6. Results of SSRT, slow strain rate tests, on notched samples of higher strength pearlitic steel under hydrogen embrittlement environmental conditions can be plotted as a single curve, geometry independent, by expressing the critical fracture parameter, this dimensionless stress, of the material as a function of the local strain rate, this dimensionless strain or strain rate in the vicinity of the notch tip, averaged in space and time. And finally, last but not least, 7, the importance of local strain rate in the vicinity of the notch tip is emphasized on representing failure loss in the slow strain rate test of different notch geometries as a function of the local strain rate in the vicinity of the notch tip, or just at the notch tip, or average in the vicinity, the notch tip strain rate, because the results for all geometries fit in the same band in this universal curve geometry independent, triaxiality independent, that represents the kinematic approach, the kinematic fracture criterion for hydrogen embrittlement of pearlitic steel notch samples. That's all. Thank you very much for your kind attention.